Hi everybody, I hope you're hearing us loud and clear, and welcome to the September webinar from Viezu. I'm Paul.
I'm Simon.
Joined by Simon. Hopefully you may have seen some of our previous webinars and I hope you've enjoyed them. You'll know if you have, in the last couple of sessions we've been particularly looking at map writing software, and we've gone through some of the main map writing software in the industry. The last one we particularly looked at the difference between Stage X and SwiftTech. Previous to that, we looked at the ECM software, and at the end of the last session, people asked what would they like us to do next. What would you like to see in the next podcast that we do? And quite a lot of people were asking for a more in-depth view of map writing. So that's exactly what we're going to bring you today. We're going to go through a diesel map in quite some detail. Hopefully this is going to be of interest to you. As always, we are live here in the room right now. Simon is going to be writing this map live for you, and you have, as always, the opportunity to please ask any questions as we go. This is meant to be as informative as it can be, so we want to pass on really as much knowledge as we can. Simon, how do people ask questions?
Two ways to ask questions. If you're looking on a laptop or desktop computer, at the top of the screen there should be a little sort of speech bubble for the Q&A. Just click on there and you can submit your question. If you're watching on a mobile device, then down at the bottom of the screen, don't press the red hang up button, but just next to it there's three little dots. If you press that, again you'll see the Q&A prompt. You can press that and then submit your questions.
Okay, we normally prattle on quite a bit at the beginning of these sessions, but I know we've got a lot to cover here. We're going to struggle to get it in the hour, but we're going to do our absolute best. But please do ask those questions. It's really important to us to get your feedback and your questions. Just to recap what we're going to do, we're going to do a brief introduction of how we approach map writing when we've got a car to tune. How do we approach that? We're going to go through the map identification. We want to identify the maps we want to be changing, which maps we do change, which maps we don't. We're then going to go straight into stage one performance tuning on a diesel vehicle, and Simon will give us a bit more detail about the vehicle as we get started, and then how we write that file and how we write that file to a vehicle. So hold on, get yourself comfortable. Here we go. Simon, what have we got?
So we're going to be doing a 2-litre diesel Volkswagen Audi group car.
Very common vehicle.
Yep. Covers a broad spectrum of engines from the VAG group, and the logic and methodology we're going to go through today and through our other courses on the remap101.co.uk website, same as with in-house classes. The methodology is the important thing to take away because it can be applied to a range of diesel vehicles. One of the key things when it comes to tuning is it's not about just that one specific vehicle, it's the logic we apply to it that can be then transferred to a big rig diesel or a smaller cylinder generator diesel, for example.
So what you're saying is we're not going to show someone how to write a single ECU type. This is a process that in theory you can apply to lots of different ECUs.
And that's key. This isn't just for this ECU. Whilst we will be going through this example, you can take away the logic and methodology we're doing today and start to apply that to your tuning on other vehicles as well. Okay.
Got a lot to cover. Are we going to be okay for the hour?
We will be okay for the hour.
As long as I don't ask too many daft questions.
Trusty pen and paper at the side as well. And part of the reason we do that is as we go through any ECU file, it's important that you do take notes as you go through. So even if you're watching there, if you've got the ability, take some notes as you go through. Anything that's important for you, anything that's a bit of information you've not seen or heard before. Hopefully there'll be a lot of that for you in this webinar, but do have your pen and paper ready to take notes. We're going to get through this. We're going to start on ECM in a moment with what we call our investigation phase, as you just mentioned. What that basically entails is exploring the maps inside the ECU driver, inside of ECM Titanium, understanding what the standard ECU is requesting, so basically the stock strategy, how much torque, how much fuel, how much boost is being requested, and then understanding from the data inside that ECU how much potential there is within the actual ECU itself. So it's sometimes misunderstood that with tuning we're creating extra power the engine was never designed for.
Sure.
But actually what we're doing is restoring that power that was already there in the engine to begin with, in a similar way that manufacturers and dealers will do sports models or uprated limited edition models. It's kind of what we're doing with the ECU tuning. We're looking at those key markers inside the maps, those hidden little secrets and bits of information to unlock its full safe stage one tuning potential.
As you know, as Simon just said, there's going to be a lot of information. I will quickly just add, if you're not writing this down or you worry about how much information we're giving over and how quickly it's coming over, this whole session will be on YouTube as soon as tomorrow, so you can watch it again. If you missed anything or you didn't quite catch it and you're not making notes, you'll have an ability to watch it on YouTube again and again. So it's going to be stored for you there too. Okay. Let's dive in.
So just before we get the ECM Titanium open and we jump to that screen, a couple of things to just cover off. Remember, ECM Titanium is ideally suited to the KES tool. You can use files from other tools with ECM Titanium, as it's now updated what they call an offset. So that's to do with the drivers. You could put an auto-tuner file into ECM, and with the correct offset to adjust the map locations.
That's quite a new change. When did that come?
It's coming recently. It's quite a new update in there.
Because I've always been telling people, yeah, if you've got an auto-tuner, ECM might not do it.
Unless you're comfortable and familiar with it, it can be quite an advanced technique. You've got to know the offset. So you kind of need to know the answer for the question before you ask the question.
Okay.
However, remember, Alientech support is there and they can point in the right direction for the correct driver. So the basis, you've got the vehicle in, you've diagnostic checked it, make sure it's a good, fit and healthy vehicle for tuning. Ideally, if you've got a dyno, you've benchmarked the vehicle to make sure the standard vehicle is performing as you expect.
Yeah.
And you've even got some data logs on there to ensure that it's boosting as you expect and all the various parameters of the engine are working in their optimum sort of fashion. They're working as you expect them to be.
So we think we've got ourselves a healthy vehicle because it's gone through that and now we're ready. Yeah.
That is, yes. So we're going to jump into ECM Titanium now. The wonders of magic, the screen should change. We're not going to go through the whole driver search process. If you're interested in that in more detail, we do have this online with our online ECM diesel tuning courses on Remap 101. But for now, we're jumping straight into the map pack of the driver inside of ECM Titanium for this 2-litre diesel. Two key pieces of information we need before we begin: the standard horsepower and, most importantly, the stock torque output of the vehicle. That's key for any diesel tuning, that we know this information. The stock torque on this vehicle is 320 Newton meters. And I can hear the question brewing from Paul already: why do we need to know that? Well, those are the values we're going to be looking for inside of the ECU to see if we can find the maps that are holding the vehicle back at 320 Newton meters, and also what the potential is inside of the driver itself. So the first place we're going to start is going to be our torque request maps. So these are the maps where you request an amount of torque based on the throttle input. I'm just going to open that map up now. RPM down one side of the map table, and we have our pedal percentage across the top.
Just have to ask, I know you're busy, I know you've got a lot to cover. Why are we starting here?
We're starting here because as the driver of the vehicle, not the ECM driver, but the driver of the vehicle, this is the first place that you have any real input on what the vehicle is doing.
Okay.
So we know what it's limited to. We've just checked the figures on the vehicle. We've dyno tested it and data logged it. We can see it's doing approximately 320 Newton meters. So the first map table we're going to look at on this torque-based strategy ECU is the request map. If our request is only 320 Newton meters, we haven't got much left on the table to work with.
Understood.
So the request map is key for two things. One, so we can see what's been asked for, and two, so we can start to look at some of the potential inside of the ECU.
Okay, makes sense.
So we're going to focus for this. Obviously, we've only got an hour, a little bit less than that now, to cover all of the maps that we need for the investigation and the modifications. So we're going to focus on the areas we need for stage 1 performance tuning. Now, in this particular map, we're going to be looking at the last column in the table, which is where 100% pedal is, where we're going to be requesting that maximum performance from the vehicle. Other areas inside of the table can be modified for different reasons, maybe economy tuning, it may be a specific towing map or an off-road vehicle you're trying to adjust the amount of engine braking on. We're going to focus on that top end of the table for the stage 1 tuning because that's where we want to generate more power, that's where we want the extra performance. So at this point, we're going to look at the values in this last column, and as we follow the RPM down on the left-hand side to around about 2000 RPM, which is where our stock peak torque would be. Again, that's why the dyno and data logging is really important when it comes to tuning. We can see we have a value of 430 Newton meters of torque. Already way above that 320 limiter that we believe the car's got from our testing and the figures. What we're going to do here is we're going to take that 2000 RPM and we're going to use that as our point of reference for the different maps we look at. This is a really key technique when it comes to tuning. Not just looking at the maximum values, we've got 460 up at the top here, but actually referencing these values against a real world measurable RPM point, such as where the peak torque is. That means on the other maps we have a consistent point of reference to check what the turbo's doing, the fueling, and of course the torque limiters. So you notice I have my notepad out. The first thing I'm going to put down is my torque request at 2000 RPM as 430 Newton meters. Now, as we go through this and we look at the next map and subsequent maps in this investigation, we're also going to make note of any larger values we see in the table, as these could be an indication of how much extra is available inside of the engine on top of the normal request. So I'll also put down in the top corner of my page 460 Newton meters of torque. Close that map. Now you'll notice there's multiple request maps here. Now this is part of the ECU strategy. They could be for different settings on the vehicle. If you think sport, eco, comfort mode on some vehicles. You could have some that are for all-wheel drive versus two-wheel drive. The strategy isn't always labelled clearly inside of the file, and even if you're using software like Winolds or the Damos, it will not always tell you the exact reason that there are so many of those maps. However, for time, we're not going to look at each and every one of them because they have similar values across each of those tables. So this allows us to move on to the next set of maps inside of the engine torque.
Can I just presume though, if we were tuning this one for real, we would go through each of those maps?
The next words out of my mouth, yes. Obviously, every single map inside of the ECM driver is worthwhile looking at, checking and investigating to ensure you have all the data you need and there's no sort of curveballs hidden inside of the ECU that you're going to come across. I will just open the next one just to show. Again, we can see the same values in there.
Okay.
So if we've looked at our request, it now makes sense that we look at our limitation. If we're asking for X amount of torque, well, we need to see where our limiters sit within that. You'll notice in this particular driver, and it's quite common in many diesel drivers, that you'll see a number of torque limiter maps. We're going to start at the first one here, our limiter of maximum torque. It's a little 1x1 map.
Oh, it's tiny.
It's
really
a very
tiny.
small map, 1x1. But we can see we have 411 newton meters, and it's the first map as well that shows that there's two tables here. So there's basically two maps been identified. They've been bundled together inside of ECM for our convenience. And just by pressing the page down key, we can swap to the second map.
Okay.
So we can see here we have two values. We've got 411 newton meters and 500. Now with a bit of common sense, we can probably see that we're not going to take the car from 320 to 500 newton meters. So the only value I'm really interested in at this point is from map 1, which is 411. The reason I'm interested in that value as well is because it's in line with our torque request. 430 for request, 411 for the first limiter. This could be the first clue as to how far we could push the vehicle safely. Next map down, we can see shows 420 newton meters. So as part of the investigation process, we're just going through and identifying the values that are inside the ECU and anything that is relevant to us for tuning. This is a really important map on the screen now. We've got another torque limiter, but it's lower than our stock torque value. So this could be a very important map for a certain operating condition. Could be a limp mode or a slightly reduced power mode. Could be for the engine's not up to temperature. But it's not the stock maximum output of the engine, so we can move past that limiter.
So you wouldn't change that one because it looks like it's some sort of limiting map.
Correct, yeah. It's already lower than the standard vehicle runs.
So it's special conditions.
Yeah, we're looking at tuning where the vehicle is operating in its normal conditions.
Understood.
And that last one we just saw there was 500 newton meters. Again, a little bit too high. Down to number 5, we can see another one at 400 newton meters. So we'll take note of that. Number 6, 320. What's the standard torque output of the carpool?
360. Was I listening?
Not the tuner. 320 newton meters.
320. Ah, I got you. Right.
So, key limiter there. You'll see in a number of ECUs, you won't often get the exact torque value in the table, but you'll have values that are either side of it, depending on how the map has been developed. What we're looking for is something that fits around those standard factory figures.
Got you. Understood.
We can see here we have 300 newton meters. So again, very important map for a specific reason, but not for what we're looking for. Now the next map down is a bigger torque limiter. This is a 4x24. This is our torque limiter over APS. APS standing for atmospheric pressure.
Yeah.
And we can see we have a larger torque limiter map with values ranging from 320, 330, up to about 350. Anyone that's familiar with this platform or has tuned a number of diesel vehicles will know the bigger the map, typically the more important it is for controlling the vehicle.
Right.
It's operating in a wider RPM range, a wider sensory input on there. So I'll look at the values here, and the closest one to sea level we have at 900 millibar atmospheric pressure, and at 2000 RPM we have 350 newton meters. So we'll take note of that. I'll have a quick look at this one in the 3D as well. And the reason I'm going to do that is because this represents typically the curve that you would see on your dyno, or if you're data logging. Torque spikes up, holds, and then starts to drop off as the RPM increases. couple more limiters to look at, and we have limiter number 8, again 400 Newton meters. You see here, just a flat map. There's no curvature to this, but the values are still important for the tuning. And then we have 2 maps that we're not going to touch for performance tuning for stage 1, but these are relevant if you do some more intermediate to advanced tuning, which is to do with things like hot start. If you ever heard of hot start fixes or hot start requests, it's these 2 maps you look at here, because they're the ones that control the engine during cranking. One map has values in all the fields, the other one has a few values missing, which is what causes the hot start issues. Torque limiter for vehicle speed. Now, 3,276 Newton meters. This does not mean it's going to be like the Starship Enterprise and have ridiculous amounts of power and torque. What it's saying here is the map table exists in the ECU, but it's not doing anything for the strategy. The ECU isn't using this table, so the figures have been put very, very high so that no strategy or anything accidentally activates it. And if it does, it doesn't limit the torque in any way. Again, limiter number 9, we have 3,000 Newton meters. And we've got similar for the gears. I'm just going to pick the 4th one as an example. We have gear limiters set very, very high. You'll typically see this in ECUs where there's a manual and an automatic version of transmission. If it's a manual, you won't see the torque limiters being activated in here. If it's an automatic, you'll typically see maybe 300, 400 Newton meters, depending on the gear.
Real figures.
And that actually completes our engine torque. A lot of maps. Spoke probably quite quickly on a couple of them, but you can see out of that we've taken 2, 4, 6, 7 maps we've taken values from out of the 30 that were there. So this is another key thing as well. Don't be overwhelmed by the amount of maps that appear on the screen. You don't need to change every map for a good tune. You just need to change the maps that are required.
But I think it's very clearly you've shown us some maps there that we don't need to change, so that made a lot of sense. So don't change everything, change what you need to change to get the result.
Yeah. I'm going to move down to our injection system now. So we're doing all right for time at the moment. That's good. And we're going to look at our fuel quantity injected map. And before you ask the question, why would we look at that map? Well, this is a really interesting map when it comes to tuning, because this is one of the maps that gives us, if you like, a reference, a lookup table inside of the ECU. That lookup table converts an amount of torque to a quantity of fuel. So if I want to look at my fuel maps, how long the injector's open for, or smoke limiters, depending on the ECU, all of those fuel quantity related maps, I need to be able to tie those values together. I need to be able to say, well, at 300 Newton meters, this is how much fuel is required. This map is invaluable as a tuner. This gives you the standard data that we're running. So 320 Newton meters, I'm going to activate this map, 320 Newton meters at 2000 RPM will put us approximately here. So we can see the fueling. Remember, an ECU interpolates data. That means it's looking at multiple cells and averaging those values out. So while we don't have 320 on the screen at the top for our axis, we can see we're more to sort of the right-hand side of this area here, approximately about 50 millimeters cubed of fuel. So that's an important benchmark for me. It tells me that 320 Newton meters of torque requires 50 millimeters cubed of fuel. So when we move on to our next set of maps, we've got a benchmark now, not only for the amount of torque and a reference point for RPM, but we can start to look at the amount of fuel. So things like your rail pressure maps and your turbo maps we'll look at shortly all have fuel quantities as their axis.
Okay, I got you.
So you're starting to marry these different things together. Unfortunately, not every map just uses torque as the axis. That would make life very easy.
Sure.
But it allows us to pull those values together.
You can use the axis from one map into the next map, into the next map.
Yes, as that data point to reference and to build up an understanding of the stock strategy. The big benefit of this map is, if you notice, the torque goes all the way up to 420 Newton meters.
Okay. Which is where we're going to be tuning in that zone.
It's about where we're going to be aiming for, yeah. We can also see a fuel quantity up there as well. So between 390 and 420 Newton meters of torque, we can see 65 to 71 millimeters cubed of fuel is going to be required to support that tune.
Why is there a fuel map here for an area the car should never be in?
Because it's a really good question. Did the car, when they developed the tune for the car, did they release it with the absolute maximum it could achieve, or did they develop it with a higher amount of horsepower and then for various different reasons, marketing and climate, whatever it may be, reduce the power down before they finally sell the vehicle to the market?
Well, they've saved you a shed load of work.
They have, yes.
Because they've done
it comes almost pre-tuned.
It does. Okay, very interesting.
So we can see supporting values for a higher amount of torque, and we will note that down again. So 420 Newton meters equals approximately 71 millimeters cubed of fuel. And I say approximately because, of course, it's averaging the data through the interpolation. And we can close that map. So that map is really important as that reference point for us, as I've just mentioned. So we've got our request, we've got our limit, and we've seen kind of the recipe of how much fuel is required to deliver an amount of torque. So now we move on to looking at the supporting maps for a higher amount of torque. We've got our reference. Possibly we can do 420 Newton meters. Now we need to see if the rest of the ECU and engine supports that. Do we have the ignition for that? So that's the start of injection angle. Do we have the rail pressure? Do we have the turbo pressure for that? Does our fuel, our air, and our diesel equivalent of spark, our start of injection angle, do they all support that higher amount of torque and fuel
Or
quantity?
are they going to run out of numbers if you get into that territory?
Exactly, yes.
Okay, makes sense.
So whilst we're in the fuel area, we're going to look at our injection timing, and we're going to open the first map up, and we can see it goes to 60 millimeters cubed of fuel on our top axis. You can see here. So we'll put that down. And I use the shorthand for this that many tuners do, which is SOI, start of injection angle, called injection timing in the driver. 60 millimeters cubed. So that's looking already like we're going to be potentially limited to less than 420 or less than 390 Newton meters of torque.
Yeah, understood.
Our next one also shows 60 millimeters cubed. Quite a small map. Our next one down shows 60 as well. And then we get to the next one that, shows 65.
Oh, a little bit more.
A little bit more. So it's worthwhile, as you mentioned even at the start, Paul, looking at all of the maps that are there, investigating all of them to see where that baseline data is. Just because one says 60 doesn't mean that is your complete limit.
For all of them.
So I'm actually going to put for my SOI 65 millimeters cubed. You might ask the question, why do we look at specific maps over others? Well, if we look at the first couple, they only show 6 and 5 tables behind, grouped together. Whereas the later ones have 13 and 12 maps on there.
More important maps.
More important. There's more of them together. So the size hasn't changed necessarily, but the quantity of them has. And of course, there's a little bit of sort of correlation with the data logging.
Yeah.
Now you bring your data logs into it. What is the standard vehicle doing? Then you can look at the maps and see, it is actually using injection base map 4 because that's the only one that had the same injection values as my data logs.
Yeah.
So it's all about bringing that information together. And we do have more injection timing maps down here as well. I'm not going to look through each of them, but these are now bigger maps. They're larger maps, 16 by 12. And again, these support
up to 65.
65. So from a time point of view, I'm not going to look at each of these injection base maps, but you see the idea and the logic and the methodology that we're following along here.
So we're still just investigating here, trying to work out which of the maps we're going to select to change in a moment.
So we have an injection limiter that's showing 42.65 millimeters cubed of fuel. So that potentially could be a limitation on there. Sorry, injection base map, that's the angle, sorry. My apologies, I'm getting fuel and degrees mixed up there. 42 degrees of injection angle, really, really high value, way higher than the standard maps are operating at.
Okay.
It shows up to 60 on the fuel, but nothing that we need for tuning at this point. And we have another injection timing limiter, but again, you look how small the map is. It's only for a very specific operating range. Yeah. Nothing that we need there. And it's the fuel quantity or torque values that we're looking at for our investigation phase. These are to do with angle of injection. So there's no values we need in that map either. We're going to move on to our injection time map now, not to be confused with injection timing. So timing is your angle, injection time is the duration. People will know it as pulse width or injection duration. Again, another really important map to look at after we've looked at the previous maps that we have in sequence. The most important one being that fuel quantity injected because it told us how much fuel is required for an amount of torque. So now we can start to cross-check against this map to see if the injectors are calibrated to run that amount of fuel.
Makes sense.
So if your fuel quantity injected map says 100 millimeters cubed of fuel and we can do 1,000 Newton meters, but you look at your injection time map and it stops at 78, well, that instantly becomes a limitation.
Yeah.
So we'll put the notes down for that. Our injection time is 78 millimeters cubed. Also take note here, we can see the rail pressure on the left-hand side. This gives us a clue when we move to our rail pressure maps if we're looking at the correct rail pressure maps. If this injection time map is scaled to 1800 bar, or 1800 bar of pressure, then when we're looking at our rail pressure maps, we need to look for values that are similar to that. And again, it helps you work out which maps are the important ones that we need. Smoke limitation, I'll touch upon briefly. On older ECUs, you'll typically see fuel quantity values in here. However, as this is an EDC 17, this is controlling the smoke or the excess fuel out of the exhaust of the vehicle based on the lambda sensor readings. So an older vehicle, think EDC 15, EDC 16, mostly pre-common rail engines. They'll typically have an air quantity across the top, and they'll have fuel quantities inside the map. In this case, we've got the air across the top, and we've got a lambda value in the table itself, but nothing we need in there at the moment for our investigation phase. That actually completes our injection system and allows us to move down to the last couple of groups and maps that we need to look at. Now, EGR control, we're not touching the EGR for our stage 1 performance tune, and our limiters here. Now we've got idle limiters, we've got an RPM limiter and a limiter in neutral. Again, not required for our stage 1 performance tune. If we're trying to rev beyond the standard limiter of the engine, we're into stage 3 and beyond and hybrid turbos and things to get enough air into the engine for those points. So I'm actually going to minimize those two folder groups. So that leaves us our turbo system and our rail pressure. We're going to go and look at our turbo pressure maps here first of all. And it's important again that you look through each of the maps that appears inside of the driver.
For obvious reasons, these sound like important maps.
Yes.
I want to go faster, I need more.
This is basically how much pressure, how much air the turbo is getting into the engine. And you'll notice RPM on the left, fuel quantity across the top, and we have our turbo pressure values inside the map itself. So on here again, we can see, a bit like the SOI, our injection time map that supported 65 millimeters cubed of fuel, our turbo also supports 65 millimeters cubed of fuel. So already we should be starting to see a little bit of a pattern here. Two main important areas when we inject the fuel and how much boost is being put into the engine, how much pressure is being put in, both scale to 65 millimeters cubed of fuel. Also, the pulse width, the injection time map supports that value. You will see on most modern diesels a number of different values in the turbo pressure maps. Again, different strategies, different operating conditions. You've probably heard of a diesel particulate filter. Well, you'll find many turbo pressure maps that are used specifically for the regen function, allowing the engine to still run and operate, but reducing the boost pressure, allowing the engine to overfuel to regenerate the diesel particulate filter.
And we don't necessarily want to be changing those, certainly not on a stage 1 map.
No, I mean that's a great point, and this is one of the ways that you'll see sometimes a good map versus a poor map. A good diesel map shouldn't have any negative impact on the diesel particulate filter at all. Whereas a poor map may have changed all of the turbo pressure maps and the car goes great down the road, but has now subsequently stopped doing the regenerations because there's too much pressure through there and you have DPF faults.
But you could certainly understand someone who doesn't fully understand these maps. Turbo pressure, let's just crank them all up. What can go wrong with that? Let's give it a load more boost pressure. And you're changing the DPF system and now you've caused a problem. Yeah, I could see how that could easily happen.
So when you've got a number of these maps and you're unsure which one is the main turbo pressure map, well, don't worry, we have a limiter of turbo pressure that gives you a guide.
Okay.
So on our limiter of turbo pressure, again, we haven't got any fuel values here, but it helps us to understand which are our main turbo pressure request maps, if you like, because the turbo pressure limiter will have similar values to the maximum turbo pressure request. So we saw approximately 2,400, 2,500 millibar on our target map, and we have 2,450 millibar on our limiter. So again, helps you identify. If you're seeing a map that only says 1,300 millibar of boost,
it's not a main map.
Close the map, walk away to the next one. You don't need it. Another limiter at the bottom there. Different scaling, different inputs for the axes, but again, we can see sort of similar values. This is temperature based, which is why it's basically a correction map, if you like. So when it's running very, very cold conditions, so this will be things like your intake air temperatures, minus 20 degrees, well, you're going to get more boost pressure because, of course, the air is much denser. So our turbo system is actually quite straightforward on this. Stage 1 tune, we're not going anywhere near the VGT on there, so we're not adjusting the variable geometry of the turbo because it's got more than enough capability that we need. And again, if we do open it and have a look, what's our magic number up at the top right hand corner? 65 millimeters cubed of fuel again. So there's no need to go and modify this map. If you've not changed the turbo to something hybrid or bigger, there's nothing to change on this map for a stage 1 safe performance tune. And lastly, into our rail pressure. We're going to look at our rail pressure map before we look at our limiters. And if you're keeping up with this or watching it back on YouTube, pausing, taking some notes and watching the next bit, which is highly recommended of course, you'll see we have 1,800 bar of pressure in the bottom right hand corner of the map, which ties into our injection time map or injection duration map or pulse width that had 1,800 bar of pressure for the control, the scaling on the axis there as well. And what does the map show in the top, Paul?
It shows 65.
It shows 65. So we have that pattern now. We can see 65 millimeters cubed of fuel on our injection timing or SOI, our turbo pressure maps, and our rail. So all of the three really important key areas
tie together.
All support that higher value.
So we know we're in for tuning here. We've got some room to grow.
Yeah. So now we're going to go back to our fuel quantity injected map, and we're going to see where that puts us in terms of the torque.
Okay, so we've done a lot of investigation here, but it sounds like it's really important because I think, I guess with lots of experience you can just steam in and start changing things. But if this is a fairly new map, that is an insight how you would approach before we do any tuning, before we make any changes. That's the work that you would do to understand what your parameters are.
Yeah, you need to understand the data inside of the ECU, and it can take a little bit of time. We've gone through it quite quickly there. I am familiar with this software platform. But even if it's a brand new ECU you've never seen before, go through each of the maps and build up that, as I said, the notes I've put down on the page here. Take notes, reference points for those maps so you can understand what is the standard strategy doing and what is the potential inside of the stock ECU.
Okay. Look, there's a lot of different approaches to this, but I guess people with a little bit of experience would probably just think, yeah, whatever. Let's just start steaming in and start changing things. The classic, give it 10% more. Let's give it 10% more boost pressure. Let's give it 10% more fuel. If you haven't done that research, though, you could quickly get yourself in trouble, I guess, with that. Just give it a bit more approach.
You can. Unfortunately, diesel engines are it's a negative but a positive. Diesel engines are typically so strong compared to gasoline engines that a lot of people can get away with a really poor, rough 10%, 20%. Not sure what I'm doing. I'll just add some more to the torque limiter, and it will probably go quicker down the road. It won't last that long, and it will probably smoke out the back, and turbos will let go prematurely. A good tune on a diesel engine should run cleanly. There should be no excess smoke out of the back of the vehicle, and it should be reliable and have longevity for those standard components on there as well.
And the research you've just done is basically the foundations of starting to provide a good map.
Yes.
Okay. Is that all the research we're going to do at this point?
At that point, yeah, that completes the investigation phase.
Okay.
I said we could look through every single map, but we've been 45 minutes in total looking at every single one. We've picked out all of the key maps that we need, and we've covered across a few of them that have repetitive data in there, so we skipped across a couple of maps for that purpose.
We promised the guys some map writing. Is that where we're going next?
That's exactly where we're going now.
All right, let's take a look.
So we've completed our investigation. The last thing we have to do between our investigation and actually starting to make the modifications is decide how far we want to take this car. What is the optimum that we're looking for? Now generally, and there will be subtle differences between horsepower differences on vehicles, but generally for a 2-litre diesel engine, you'll see out there the general benchmark is 30 to 40 horsepower increase, and anywhere from sort of the high 60s of newton meters to maybe 80 newton meters of torque increase. Now this is the slightly lower version of this engine in terms of horsepower output. So when we're looking at our change, if we look at 2000 RPM, we can see our 65 millimeters cubed of fuel sits under the 390 newton meters of torque. So that gives us, 70 newton meters increase if my maths is right?
Yeah.
Now when it comes to a dyno, you will often see a slightly higher peak than we show in the maps. That's an important thing to cover off. So you may have set the cars at 320 newton meters of torque, for example, as standard. It might produce 326 or even 330 on the dyno because of what's called transient torque, that initial spike, and then it gets back under control. A bit like overboost, believe it or not, diesel engines have over torque. Very similar thing to overboost. It spikes up, gets it under control, and then holds. So whilst we're targeting 390 here, from a dyno point of view, we'd probably see about 400, maybe even 405 newton meters on a healthy car.
That's a nice figure.
And remember, we're taking the standard values that are inside this ECU. and maximising the engine performance based on the data that's there. So we are looking at 390 Newton meters, 65 millimetres cubed of fuel as our go-to target.
Yep.
So we're going to close the map. We're going to go up, and we're going to go back through the ECU in the same logical fashion that we did our investigation.
Yep.
And that's really key. Go back through the maps in the same order. If you start jumping around to different maps and go, oh, I know I'm going to do this to the boost because I always do it to the boost, you'll easily miss one. And then the phone goes, or a customer comes in, or a technician knocks on the door, and you've lost where you are. So follow that same logical process and order through. So we're going to open our torque request map. Now, our torque request map actually sits above that 400 Newton meters, 390, 400 that we're aiming for, but we're a lot closer to that value now. As we can see, the standard requests were way up and above what the standard vehicle could do. So as a kind of housekeeping modification here, we can take that peak value of 460 and just extend it down to the very end. Yep. So we're still asking for torque at the top end. It's never going to produce 460 at 5,000 RPM, of course, but what it does is it removes that risk of our torque spiking up under a certain condition, just catching similar value to the request, and then the ECU wanting to shut everything down.
Yeah, yeah. So this is like a safety margin tune, really.
Yeah. So we're going to press edit value. We're going to type in 460 and press enter. And again, why do we do it on the 100% column? Well, 80, 60 and 40 on the throttle isn't the maximum output of the vehicle. Mm-hmm. Now, you as a tuner will have to decide based on logging and testing on the vehicle if you want to start making changes further down. But if we look at those values, we're going to go past these anyway. Mm-hmm. The standard request was already above these values, so we know we can push that 100% throttle area. You'll notice on this screen as well, we've got the option to save and exit. It's showing us the one map table, because there was only one map table available to us to tune here. And all of the copy increments onto similar maps are greyed out. Again, there was only one map table open for modification. We will cover this off in a little bit of detail when we get to one of the later maps. Quickly, you've got cancel and exit. Oh, I've made a mistake. I'm just going to cancel and come back out. Or you've also got the option of resetting the entire table back to the original values. You're not happy with what you've done. You've made 30 changes. You don't want to go back through each one and undo it. Reset it, go back in, start again. We're going to save that modification. Now, for time purposes, I'm not going to go through now and modify maps number 2, 3, 4 and 5.
Sure.
But as we said, go through and make the similar modifications to the similar maps. So like with the investigation, check each of them. On the tuning side, if it has the same values or very similar values, you must modify in a similar way for consistency. You don't know if it's using number 1 or number 2 on a Thursday afternoon on the drive home from work. Make sure you modify them in a similar way. So assuming we've got all our torque requests done, we then need to look at our limiters, of course. Mm-hmm. So we'll go back from the top. And we have a couple of map tables here. We can see on the bottom of the screen, map 1 of 2. This one's set at 410, or 411. We're going to need to creep this one up slightly as again, so it doesn't interfere with the new value that we're going to be aiming for, of 390. We're going to press
quite close.
Enter. And you might ask, well, what value do I put into here? Well, follow the logic and strategy of the ECU. We've got 460 on our request. Mm-hmm. This map sat below the stock request of 430 anyway.
I'm going to go for 500.
You could go for 500 and it removes this maps function out of the way, but we're going to keep it within the standard request.
Safe. Okay, good.
430, press enter. Now, the eagle-eyed amongst you will remember the first map said 411 and the second one said 500.
That's why I went for 500.
Yeah. We could do that, but again, we don't know the purpose of this map.
Understood.
So this could be a very important safety map. If we put it to 500, it never interferes with the engine.
But we don't know what we've done.
Correct.
Really.
So it's all about maintaining that hierarchy to the maps. Keep the order and sequence.
That's why you're the map writing guy.
So we're not going to press copy increments onto similar maps. We're going to leave the do not modify similar maps option selected, so it only modifies the first map table there. Limiter number 2, it's at 420. We could leave it at a similar value, but for consistency, we'll put this up to 430 as well. Close the map. Next limiter is already below our stock output. So we can already achieve more than this, so we don't need to modify. Limiter number 4 is above and beyond what we're already doing and what we're aiming for, so we can leave that map alone as well. Limiter number 5 is at 400, so let's take this to the same 430.
I can follow the logic, and this is makes sense. I hope you guys are getting this. I hope it's making sense to you guys. As we've already mentioned, if you see something that suddenly doesn't make sense or you want to ask a question, we are here to answer those questions. Do fire them in. Simon, I've interrupted you. Please carry on.
Really important. Single value limiter here at 320 Newton meters. That is the standard output of the vehicle.
We're going to move that one up?
We are going to move this one up, and we're going to set it to our new target that we're aiming for of 390. We could move this up to 430, and then what's going to happen is we're going to change the strategy in the ECU that it's going to start using other limiters instead of this one as the main control.
Right.
So I mentioned before, the bigger the map, the more important, but this map has an overriding value. Mm-hmm. This map is saying that the big limiter is 350 Newton meters, but I'm going to basically put the maximum clipping point in there of 320. Let's keep the hierarchy, and if we want to push further, we can with time on the dyno. As we're going to mention towards the end, the validation of your file, testing, developing, and testing and developing, you may want to increase further, but for now, we're basing this on, we've got the car, it's ran stock power, the driver says the information inside, we're going to follow that through to then get the increase that we're looking for. So we'll put that increase in there at 390. Limiter number 7, values are too small, so we can just close them up.
Mm-hmm.
Now we're on to a really important one. This is probably one of the most important maps when it comes to modifying this engine, because this is going to control the delivery of our torque.
Yeah.
The standard vehicle is going to have quite a flat torque curve because it's going to increase up, as we can see with the 3D map. It's going to increase up, then hit that 320 Newton meter point and just kind of feel very flat where the mouse is, not the pointer, and just be flat on the dyno.
Yeah.
Now we've raised the torque limiters elsewhere, we've raised our request, this map is now limiting at 350 Newton meters.
Mm-hmm.
The change you make to this map will determine how smooth or how aggressive the tune is. So we're typically aiming for a progressive tune, but if you put the values up very aggressively early on, you're going to end up with a very aggressive tune. Great for some customers, that's what they're looking for, but it can put excessive wear and tear on the drivetrain and on the components.
And I'm guessing stop the vehicle feeling quite so smooth.
Yes. So the typical areas we're going to modify, I'm just going to highlight them on the screen, is this area. From approximately 1500 RPM, which is typically where boost starts to really spool on the car, the vehicle's out of that operating or driving condition of the initial starting or changing sort of gear, that initial inertia brake point. So away from that sort of point, the vehicle's starting to accelerate up. This is where we need to make our modifications. Don't just do a flat percentage.
Sure.
It's quick and easy. We could put 10, 20, 30% on, but that's just going to exaggerate what's there and not give us any progressive feel to it. Now, in our training courses, we go into this in even more detail because there's a number of different ways you can break this map down to make those changes that you're looking for. We're going to use a sort of staged method, if you like. We're going to use an A, B, and a C method. So we're going to start with a small modification at the beginning, so we don't put a huge amount of load on the engine, build it up to our peak torque, hold it through the mid-range to our peak horsepower, and then remember, once it's hit peak horsepower, a diesel engine's really running out of steam and you're revving it for the sake of it.
Yeah.
So we then need to bring our values back down again. Quick way we do this, we're going to edit one value to 390. That's where our peak is at 2000 RPM. We're going to check with the percentage button pressed and the increase that we can see we've got an 11% increase, 11.4 there. That's really important because what we're going to do is undo that change, and then when we select the first area and right click for our interpolation, we're going to put 11.4 on the right hand side so we can scale our modification up. In this case, because it's quite a small percentage, and by small I mean it's around 10 to 15%, we're going to start with a 0 on the left.
Okay, so we were starting really smooth.
Yeah. If we're making changes here of 20 to 30% and above, we might want to start with a 5 or 10% on the left, just to give it that initial sort of first kick. We've got percentage selected. We're going to press OK. And we can see there we're at 389.9. So there, 390 Newton meters. Area B is our peak torque to our peak horsepower. And on here, it's just going to be the same maximum modification across the entire area. So we're trying to hit that peak and extend it across the RPM band as far as we can. Then area C, we're going to go to the last positive value. It's pointless modifying zeros. And we're going to do a reverse of area A. So we know our peak horsepower will be approximately 4,000 RPM, might be a little bit over. So we hold that value to 4,200 and then tail the modification back down to 0. When we look in the 3D, rotate this round, pressing the escape key, we can see we've got a nice progressive ramp up rate, as much as we can with a small amount of data that's there in the table, and it holds all the way across. So you can see there's a little bit more of a dome. Instead of it being so flat, it builds up, holds, and then drops off towards the end. And again, what we're doing with this modification with the area C, we're not trying to extend it to the maximum RPM on the engine. We're just trying to get it to rev out smoothly and progressively to that peak horsepower. I can see there was a hand being raised in the corner of the room for a question.
There's a question from Amy. Could you add a more aggressive tune to sport mode only?
Yes, you can, providing the ECU supports that. So if you've got a number of limiters that have, for example, the strategy, you've got a sport limiter or an eco limiter, depends on the ECU, but you can make changes to those particular maps. But that's about understanding the strategy that's there. You're relying, of course, on the ECM driver, so the naming conventions there, if it's got it labelled.
So you've got to be able to find the map to make a change, but if the map is labelled, in theory, you can.
Yeah, and of course, as a tuner, this is where your development, your R&D and validation comes in. You make your change, you test it, does it have the desired output you want?
Very nice. I mean, that was a really good example, actually, of a nice change in a map that shows a strong change, but smooth as well. That was a really good example.
Yeah, it's one of the few areas inside of an ECU, and we're just doing some more housekeeping here, bringing this up to 430 Newton meters from 400. It's where you've got the ability to actually apply your signature, your style of tuning. If you like more aggressive tunes, build it up more aggressively. If you like super smooth, you may go in there and start smoothing all those little undulations out. Yeah. But again, it's important, if you do that, test, and test again to make sure it doesn't have a negative impact anywhere.
Okay, nice. So we've changed, what, 5, 6 maps now?
We are 7 maps changed.
Okay.
And that is it for the torque limiters on there.
Okay.
Everything else we saw really high values. Again, out of 30 maps, we've only modified 7. So we can effectively minimise that area.
Okay.
It's done. We'll just show you quickly. So you can see the maps you modified with the dot.
Very
in the
useful,
green cell. Yeah. Again, helps you keep track. So onto our injection system here. There's 2 main areas we're going to make changes to. We want to optimise our ignition timing. We want to bring in that fueling a little bit sooner. So that helps us get the fuel into the chamber a bit sooner. We get a better combustion, bigger combustion, because it's had a little bit longer to inject the fuel. Yeah. It's a little bit like adding extra fuel without having to add extra fuel. And we're also going to make a change to our injection time map. And we'll explain that one when we get to that map in a second. So the injection timing maps we're going to look at are actually going to be our biggest ones, our 16 by 12. These are our main injection time maps. There is a general rule, and this is where the dangerous 10% appears. There's a general rule with changing these maps. We're looking at a maximum change of around about 2 to 2.5 degrees on a normal sort of passenger vehicle. Yeah. So think everything up to sort of your 3-litre diesel engines. Or around about a 10% change. So 8 to 10% or 2 to 2.5 degrees really is your maximum change. It gives you a good, safe working area to begin with. You may find you need to go more on certain vehicles, but if you start seeing changes of 4, 5, 6 degrees, you might want to double check the change you're making on a typical passenger vehicle. Yeah. Now, of course, trucks, a little bit different. We're not looking at a heavy goods vehicle here, but it's all relevant to the standard data. So a truck may have 40 degrees of timing in there, for example. So then you're looking more at the percentage rule as opposed to the physical degrees rule as your sort of area to begin with. The area we're going to modify is really sort of down in this right-hand corner here, where we're looking at our maximum output, we're looking at the maximum power and performance, and we're looking from an RPM point, not going as low as the 1500 RPM where we raised our torque limit, because again, if we put too much load down in the ECU, in the engine, we're going to potentially risk sort of overloading it. We typically start timing changes from around about 2000 RPM. And you'll notice on here, so just there, I'm going to go back to the 40 on the fuel. So I'm not going all the way down to this 30 point, which is typically our halfway point, equivalent to about 50% pedal. I'm going to our 40 millimeters cubed on the fuel, which is around about 60 to 70% pedal. Again, moving out that normal driving, cruising area into more sort of the performance range of the vehicle. This one's an easy one. With the percentage button selected at the top, we can just press page up and add our 10% onto there. If we check our values, always do, we can see our increase is 10%, but if I turn the percentage sign off, I can see I've gone a little bit higher than my sort of safe operating area, 2.88. So let's paste ORI, revert it to original, change my percentage to 8%. 8% in there, make sure my percentage symbol is highlighted, press page up, and if again I check the increase, so even with 8% on there, that didn't lock the value in. Apologies on that, put it back to original, 8%, always make sure you press the enter so the cursor isn't flashing. Got my 8% increase now, 2.3 degrees.
Okay, nice.
Always worthwhile checking all the changes you're making in the percentage view and in the increase view so you can confirm the change you've made is exactly what you want it to be, especially when you're looking at some maps like this where there's a lot of different values, a lot of movement in the table. Check those values to make sure you've had the change you wanted.
Okay.
Again, for time, I'm not going to look through each of the injection base maps here. We need to modify all the similar ones, of course. We'll move on to the next map in this group.
Mm-hmm.
And that's going to be our injection time map. Now this map, some people will choose to change after they've changed the turbo pressure. You can change it while you're in this area, and the reason we would modify this typically after our turbo pressure maps have been changed is because if we're asking for more air, we know our axis is fuel based, so we're asking for more air from the turbo system, which means technically we might be leaning the mixture out slightly.
Right.
So more boost is great, but we've got to have the fuel to support it.
Sure.
It's all a balancing act with inside the ECU. You'll also see on the left-hand side, I've got no fixed point to start from. I've got no RPM to reference against. I'll look at my fueling across the top, and I can make some changes in this bottom left-hand corner, maybe to the 36 on the fuel, maybe 48, similar to our SOI injection time map just. But I haven't got a fixed point for the rail pressure. I don't know what rail pressure to start at. There's no point starting at 1500 or 1800 because at that point, I've run out of RPM. That maximum pressure is at the maximum RPM point. So whilst we will make a change to this, this shows why it's important to understand the references for these map tables, because we're going to need to look at one of them before we can make a change to it. So let's go down to our rail pressure because we need that value. On our rail pressure map, we can see our maximum rail pressure is at the top end of the table. But as we come up here and we look at, was it 1500 RPM or even 2000 RPM, we can see at 40 on the fuel, same as we did our injection timing map, we can see we have the values of rail pressure here. So if we follow suit and we make our change either at 15 or 2000 RPM, depending how aggressive you want that tune to be low down, we can then cross-reference that against our rail pressure on our pulse width map.
Yeah, that makes sense.
So we can hop into our pulse width map quickly, our injection time. We can look, we've got 1200 bar on here. Let's move across. And we'll go to the 36 on the fuel. It's the closest value we've got to the 40.
Yep.
Come into here, and we're going to make the same change here as we did on our SOI map. So that's our injection timing map. We're making an 8% increase here because we're going to follow that change along with our turbo pressure map. It's all about consistency across the engine.
It's almost like you know what you're doing.
There is logic to the madness. You may find on a particular vehicle you need to go a bit stronger on the fueling. You may find on a particular vehicle you may need to go a little bit less than that on the fueling. But this is where your validation comes in when you're dyno testing or road testing in controlled conditions with your data logging, making sure the vehicle is responding how you expect it to respond.
Very good.
So let's minimise the fuel. I will look at our rail pressure as we were just in that map.
Yeah.
So for ease, there's a different way you can modify the rail pressure depending on your style and preference. Because this pressure is so high, it's 1,800 bar of pressure. That's quite a lot. It's enough to cut through most objects, the amount of pressure going through there. Not particularly a big fan of increasing the maximum rail pressure massively, but we'll modify in a similar area to the other maps, and then we'll do a little bit of housekeeping. We'll trim the maximum values back down so we don't exceed that 1,800. Very important for some vehicles, they have mechanical release valves for the rail pressure. So even if you map it to a higher value, you can actually find that in some cases, the mechanics on the vehicle will just release that excess pressure, and you may actually find yourself on a trip to the main dealer to get that reset.
Right.
So we don't like to exceed the maximum values.
No, makes sense.
4 to 5% is typically a good working area. Depends on the vehicle. Again, data logging is important on there, but about 4% on this will be good. We'll make our increase, and you'll notice I've just broken the rule I've said. I've gone above 1,800.
Yeah.
So what I then simply do is highlight any value that's gone above that, and I'm not going to undo the value or paste original, because it might have been a little bit lower than 1,800 to start with, but now has exceeded it. So I'll edit those values back to 1,800. So we can see in this case only actually one of them is modified. This one here, you can see it in the red, but it's a worthwhile exercise to do. Again, you can end up with random sporadic errors on the vehicle when you've made changes to that map but you haven't clipped the values back down. So for ease on this one,
that's a really good lesson.
I'm going to copy the increments onto the similar maps just to show you this function. We've got absolute or percentage. Well, we did a percentage change, but we also did a manual change as well afterwards. If we just did percentage, which we'll show on the turbo pressure in a second, we could just select the percentage, run the correlation. Now the Pearson correlation is a mathematical correlation to say, hey, are the values similar? Yes, I'll make those changes on there. And you can also set a threshold of percentage, how close they are for making those changes. In this case, we're going to put it on percentage. We'll leave the correlation and press OK. But it's worthwhile going back in there, going through each of the maps and double checking they have had the desired change that you're looking for. Because I've made the change in that way, I don't need to touch the limiters.
Yeah.
And again, we do have another rail pressure map, but I'm conscious of time. I'm not going to go in and make the same change on that one. But please do make sure you're consistent in your changes that you make. Going to jump into our turbo pressure now. I'm going to look at our first turbo pressure map. You can probably guess where the change is going to be. We're going to be looking in around that either 1500 to 2000 RPM point down to the 40 on the fuel. Now you may wonder why this one we do at 1500 RPM, whereas things like this injection angle we did at 2000.
Yeah.
If you look, we're already hitting peak boost at 2000 RPM. Why? Because that's where our peak torque is. We've already achieved it. If we wait until that point to make our change, it's too late. We've hit peak torque, and then the turbo is then playing catch up as opposed to helping to propel the vehicle further.
Makes perfect sense.
You can make changes on this table in a couple of different ways. You can use a flat percentage increase. You could use an absolute increase and say I want 200 millibar. And you can also scale the changes. We know we've done 8% on the other maps, such as our injection angle and our injection time. And on here, we're going to keep that same 8%, but we're going to halve it and go to 4 on the left-hand side. So we start to spool the boost up before we hit that maximum fueling. If we just wait until the very end of the map, again, same way if we wait too late in the RPM, we've run out of time to actually get the pressure in there that we're looking for. 8% increase was our maximum. We'll close that. Again, we can copy the changes onto our similar maps. And again, conscious of time now, we've got a number of maps in there. Go through and only modify the ones that have similar values.
Yeah.
That takes us to our boost pressure limiter. Now in reality, if you know the car's running only at sea level, you can make the change to this map from 1500 RPM if you wanted and all the way down. But atmospheric pressure sensors are well renowned for being very inaccurate. So for ease on here, you'll find a lot of people will select the entire map. And you think, well, we've gone below 1500 RPM. Well, that's fine because we're not producing any boost below 1500 RPM.
Yep.
There is nothing worse than making your change and accidentally selecting 1750 and 800 millibar and actually finding your car is running down here and you haven't made the turbo change. So this is a nice safe map that we can make the change as just a flat percentage across it, 8 in each corner. And I did see a hand go up in the corner of my eye. There was a question, I believe, Gavin?
Yeah, this is from David. Why didn't you extend the injection time map for a larger dose of fuel?
Okay, I think we made a change. I think we increased it by 8% on there, in line with the same change that we make into our turbo system now. Maybe I've not understood that one. So if you want to come back with an update to that or follow up to that question, Dawood, we'll pick that up either in this webinar. I'm conscious we're running a little bit over now, or I can pick it up and answer afterwards and share.
But it is a map that you would change.
It is a map that you would change, yeah.
And in this example, we would normally change it 8%.
Yep. So in this example, sorry, just double clicking there. In this example, you can see our injection time. We changed on here by 8%.
Okay.
If you remember, we had to get the rail pressure to cross check it.
Hopefully that answered the question. If not, let us know and we'll reply to you after the session.
So it's a whistle-stop tour through. Spoke very quickly. A number of maps we've looked across there. Obviously, look at these in depth. Check every map inside of the driver. Make sure you're comfortable with the values that are there. Once you've completed all of your changes, you've validated them, you're happy with, you've got all the maps that you need. It's then a case of simply saving the file and exporting it to your computer, your desktop or network drive, whatever you're using, and then taking it to the car and writing it back with the same tool that you read it with. Then you're into your validation. Upload it, test it, whether it's road or dyno, with your data logs. Is the vehicle responding how you want? Is the tune too aggressive and you're getting a little bit of torque judder through the drivetrain, in which case soften the tune up. If it feels like it could be a little bit more responsive, then bring your tuning in a little bit stronger low down, maybe increase some of the values on there. It's all about validation, double checking, triple checking the tune you've uploaded is responding how you expect it to respond. Another question there, Gavin? So pointing at the screen as if there's a question on there. That is a whistle-stop tour of stage one
tune on a diesel vehicle. Guys, I hope you really enjoyed that. I know we covered a lot of ground. If you've got questions or if you watch this tomorrow and still have questions, please do fire them into us. We are here to help. I'll do the cheesy sales pitch line 2. Of course, we do much more in-depth training on this too. These sessions are not about trying to sell our training courses or software or anything else. It is genuinely about passing knowledge. But if you like what you see or you want to know any more information, we do 3-day courses, 5-day courses, both on gasoline and diesel vehicles. We train on most of the software in the industry too. ECM, of course, is one of our staple go-tos, as is WinOLS. And if you're at the SEMA show this year, coming up in just 4 or 5 weeks from now, we are going to be at SEMA. We're going to be on stand doing demonstrations on all of the software, so you can join us on stand for demonstrations. And both before and after SEMA, we have WinOLS training for diesel and gasoline vehicles too. So if you want to come on one of our courses, please do book. Diesel is just about full now. We've still got some space on gasoline. And we run courses every single month, both in the UK, we're often in the US, and around the world, in fact, including Dubai, Singapore, South Africa, and various other countries that we train in. But in the meantime, fire your questions in. We're here to help. Simon, we are slightly just running over, but we've almost got it to the hour. I will quickly add, in the next session, we're going to do exactly the same exercise in about 4 or 5 weeks' time, and we're going to do that on a gasoline vehicle. So we're going to do same exercise but on gasoline, so you'll have both maps demonstrated. Anything else you want to cover tonight, Si?
No, I think you've really covered it really quickly on there. I know it's a whistle-stop tour, as I said through there. We've run through the maps very quickly. I've talked very quickly on there. The diesel ECM titanium course, so our Alientech titanium 3.0 diesel online tuning course, is on remap101.co.uk, which takes you through a similar diesel ECU. That is broken down over 4 modules, broken down into 15-minute bite-sized chunks. So you've got a little bit of a breather in between the next one that you start. But that is over 4 hours of training content, just to show you the in-depth nature of what we do and how much into detail we go through there. And we cover a number of different tuning and modification approaches and styles through that course as well.
Great. Okay, great. I mean, I hope you guys have enjoyed that. As I say, fire in any questions, even after the session. We'll be happy to help. Other than that, Si, anything else you want to close on today?
No, I think we've covered everything there. Biggest thing, take your time, look at the maps, and importantly, be consistent. If you're unsure, we're here to help. Fire questions over. If you're unsure on a map, drop us a note, drop us an email. We're happy to help and support people out there in the tuning industry.
All right. Well, as always, it's good night from him.
It's good night from him.
See you guys.
Thanks.